I'm Dan Pipp with Geoprobe Systems. I'm going to introduce to you a new technology that we're using for aquifer measurements. And this technology is a direct push nuclear magnetic resonance, or NMR. The technology has been used in many different industries, including analytical chemistry for the determination of molecular structure. In medical fields, it's used if anybody's ever had an MRI to determine where you're injured or if there's an illness. Same technology is used there, as well as in the oil fields. For decades, it's been used to determine where good producing oil reservoirs are for the oil companies. Here we've partnered recently with Vista Clara out of the Seattle, Washington area to be able to bring this technology to direct push applications with common size drilling machines and drill rods. So magnetic resonance technology actually is measuring hydrogen on a water molecule. And how this occurs is the tool has magnets in it, and the hydrogen proton actually has a magnetic moment to it. So you can actually align the hydrogen protons in phase, and then with a secondary magnetic coil in the system, pulse that, and it'll actually cause a precession or a rotation of the hydrogen proton. And that actually will give off a signal which the coil will measure. So the measurements that the NMR gets from the subsurface, from the water molecule, actually gives us information about the aquifer, about the porosity. We receive a signal back on the magnetic coil, and that signal, the intensity of the signal, is directly related to the amount of water content in the subsurface. And then as the rotation slowly depletes on the hydrogen nuclei, the faster that depletes or loses its energy is directly related to the pore size of the subsurface. So in tighter formations, smaller formations, silts, clays, it's going to deplete very rapidly, whereas if you have a sandy, gravelly aquifer, it's going to be able to rotate or precess for a longer period of time. We're talking just fractions of seconds that we're looking at this. But the instrumentation is able to measure this, and we can get information on the subsurface aquifer on porosity, of water content, of the grain size distribution. So if we're in, that porosity can be translated into mobile water, capillary water, or bound water. So whether it's in like sand, silts, or clays, and which can be very useful for the hydrogeologists in determining information about contaminant migration, and the pathways and that sort of thing. We also can, with the tool and the software, determine hydraulic connectivity, which within the NMR tool, we're able to get K values that are going to be beyond what our hydraulic profiling tool, or HBT, can do. So both on the lower end and the upper end, it can go beyond what HBT can see. The information from the NMR, while of interest to the environmental engineers, also can be of interest to the geotechnical engineer. The porosity can influence the bearing capacity of soils, and so that can be of interest in construction or shoreline, as well as mine tailings. We've also seen interest in local water boards trying to do some managed aquifer recharge. So these are the primary components of the direct push NMR. We have the DART probe, which is where the circuit boards are, the magnets. We have a couple different magnet sections down here, magnet arrays, top and bottom, and then there's a magnetic coil in the center of that where the measurements being made. We have our surface station, which operates off of a pair of 12-volt batteries connected in in series for 24 volts to power the unit. The logging cable is going to connect to that, and when we're about to deploy it, we'll actually have the logging cable spread out on the surface, on the ground surface, and of course that will be connected to the dart. So the first thing we're going to do to deploy the NMR tool is to drive empty casing 2 1/4 inch rods in the ground. I have a shorter rod to begin with. We may use 5-foot rods. Here's a shorter 3-foot. You could use a 2-foot rod. It's helpful for when we get the tool all the way out, so that we can more easily handle the tool at the end of the log. We have our expendable point in the special point holder, which is going to catch the dart as it's being retracted and pull it back to the surface. One other thing that's very important with the NMR, direct push NMR tool, is that you have your 2 1/4 inch rods are new, or you go through them meticulously to make sure that there's no mushrooming on the inside edge of the male rod or the female rod. There's very little annular space between the dart, especially at the collar, where we join the cable to the dart. And it has happened quite frequently when people have gone out, if they just grab used probe rod off the shelf and don't go through it, that the dart gets stuck and we cannot get it to the bottom to be able to actually deploy it. Everything has to get pulled out, and you have to go through the rods. Spend a lot of time doing that before it'll actually work. The next step is going to be to deploy the dart down the rods. So as I said, you're going to have your logging cable attached. We have a special push connector, push collar. It goes just above the connector for the cable. And this actually has a adapter fitting where we have a reverse thread connector for our extension rods that are commonly used with SB16 and some of our older tools. But that will go in, it's reverse thread. Once everything is in place, you're going to take this and insert it and put it into the rods. One thing that's actually quite interesting and nice about the NMR tool with the magnets in here, we have little problem losing these down the rods. So the magnets will hold on to the rods, and you'll have to push pretty good to get this down to the bottom. When we're in the next interval, our extension rods will just click in here. It's probably a good idea if you need to rotate the extension rod to get it to fit in there, that you alternate left and right which way you're rotating it, so we don't unthread this prematurely. When the tool's at the bottom of the rods, you'll want to add water so that, especially if you're in a sandy formation where you begin, you don't get any sand heave or anything that'll come up into the rods and lock the tool in a position where it's not fully deployed. At this point, we need to hold the extension rods down, keeping the dart on top of the expendable point, and then retract the outer rods until the shoe engages with the top coupler of the dart and cable. And then we can turn the extension rods clockwise to disengage from the push collar and remove the extension rods. The logging process is going to be occurring as we retract the rods out of the ground. The measurement interval of the magnetic coil is about 4.5 inches. We commonly will stop every 6 inches and take measurements, which currently are lasting just under 90 seconds per interval. As the log is being created, as we're retracting the rods, we will have software, which is both acquiring the data, and then there's a viewing software that can also be run so we can actually see the data, the process data, as it is being created as we're retracting the rods out. Some of the parameters that we're seeing are the T2 distribution, which has to do with the length of time the rotation of the nuclei is going on. The longer that happens, the more permeable the formation is. We also have a column for water content, and typically if you have a fully saturated formation, your water content values are going to be in the neighborhood of 35, 40, maybe 50%, because the soil particles are going to take up the rest of the space. From the T2 relaxation times, we can interpret whether or not that the water content is held up in either mobile, capillary, or bound formations, if the water is that. And then we also will have a couple different models of hydraulic conductivity.